Oh no. All right. Happy Thursday. So it feels like the quarter is flying by, so we're already at the end of week 3. So just a reminder, we don't need abstracts this quarter. So I've been still getting like 1 or 2 abstracts from people, and while they're wonderful to read, again, we'll channel that energy into our paper instead. And so make sure you get the paper topic to me, again, through Blackboard. Unless you really, really want to hand it in by paper, that's fine. But select your paper topic. Again, it's due officially by next Monday. You can always take an extra day if you need, but make sure you're thinking about this. Ask me for help. Like I said, if you run into paywalls or just want to talk about your paper and how to structure it. And then other just announcements. I think we're going to have an Earth Club meeting tomorrow, which is basically Science Outreach Club. So if you want to join, I think tentatively like 1 p.m. and HEC. Last time we said 319, but it might be 314. But somewhere on the 3rd floor you'll find us. So if you want to join your classmates, Alexis and Sam are in there, and we're going to be planning our events. All right, other questions, comments? So let's continue with, we'll kind of finish our lecture stuff, and then I brought some stuff to play with for demos here today. All right, so we were looking at our partial pressures. And so with our partial pressures, and this was from lab, right? So remember, we were collecting our gas over water. And so this is a common technique. And so it mentions here, right, gases are often collected by having them displace water from a container. And so we saw this in lab, and we had to correct for it. And that was part of, right, the equations where it's just kind of like, do this, do this, do that. Well, now we're understanding why. And so we saw with our equation that there's also water vapor in that gas, right? So some amount of water molecules are in the gas phase. There's just a little equilibrium, right? You guys understand that. So even you can leave a cup out of water and eventually it'll evaporate over time, even though it's not at the boiling point. So again, showing us that there's some sort of vapor pressure that those molecules are leaving. And so like I'd mentioned in lab, we can use a table. And so this is commonly used, or we could look up the relationship. So every substance has this curve. So our vapor pressure curve. And like I had mentioned, what defines our boiling point is when our vapor pressure reaches, right, atmospheric pressure. So that's why water is said to boil at 100 degrees Celsius, since that is when it reaches 760 millimeters of mercury, which is, again, equal to 1 atm. And so again, we saw that, and it was easy to kind of ask Google for a more precise relationship. Again, this is just all built off of a relationship curve. And so I believe this is all determined experimentally for the most part. Lost my... All right, so now let's look at temperatures. And so I think we had kind of thrown the equation on there on Tuesday. So the idea is, of course, we want to relate our average kinetic energy of our gas molecules, and it depends upon the average mass and velocity. And so gases in the same container, they have the same temperature, therefore, right, they have the same kinetic energy. And so if they have different masses, the only way for them to have the same kinetic energy is for them to have different average velocities. And so we're given this relationship here. And so what we often find is lighter particles will have an average faster velocity than more massive particles. And so this starts to get into kind of the practical issues with like hydrogen fuel, for instance. So right, hydrogen is the tiniest molecule, and so it's going to be moving fast. It's also going to have the highest tendency to leak, right? So comparing why we don't have a bunch of hydrogen pipes everywhere piping over hydrogen. Well, of course, it's obviously hard to keep it in the gaseous or the liquid state, excuse me. It goes to a gas pretty quickly, but then it's also going to be escaping. So it's not like, you know, oil pipelines where that works a lot better for transportation of fuel. And so then looking at this formula, we can calculate our root mean square velocity in units of meters per second, but that means that our molar mass is in kilograms per mole when we use it in this formula. So we'll practice that. And so then this is just kind of graphically showing what we're saying. Again, we have our distribution with our kinetic energy. And so now we're just saying, okay, we take a snapshot of all our molecules. Well, the fastest ones are going to be the lightest ones, and so that's why hydrogen has the widest distribution, right? So it has the ones that are going to be moving the fastest. But again, if we take a snapshot at any moment in time, some of them could be not moving. And then we have our average, velocity here. And then as they get heavier, their curve tightens up a little, and then of course, their average root mean square velocity decreases. So oxygen, you can just compare where its average velocity is versus hydrogen. And so then just plugging in how to solve these. So this is just a different form of kind of our root mean square velocity, where this is Avogadro's number. The R that's given is now our energy gas constant to match with our energy. And so again, we get this molar mass in kilograms with our equation here. All right, so let's see how to apply this then. And so I would just use this form of our equation. And so it asks us to calculate our root mean square velocity of oxygen molecules at 25 degrees Celsius. And so I'll rewrite kind of the easier form of our formula. So 3RT over M, but remember M is going to be kilograms per mole for our molar mass. So see if you can plug this in now. R, 8.314 for the matching units. So yeah, make sure you convert to Kelvin as well. That was a question. And then let's just go over what we want for our mass. So right, if we look at our molar mass for oxygen normally, right, we would say 32 grams per mole. But now it says, well, let's just report that value in kilograms being the correct unit, right, for energy. So then that just means it's 0.032 kilograms per mole. And so now we can plug all these values in to our formula. So our average root mean square velocity is our square root of 3 times r times our temperature in Kelvin over 0.032. And actually fired up my calculator today. Well, now I've lost my mouse. There it is. And so you guys can tell me in the chat what y'all get or yell at me. And so what do y'all get for this one? So you said 480 what? So 482 meters per second. Excellent. And then I see pretty close in the chat. Yeah, maybe just double check we didn't punch a tiny number in wrong. Double check the gas constant, 8.314. Good. Any questions on? Yeah. So let's see. So our gas units. So now I have to look up. So our gas constant units are joules per Kelvin mole, which is also, right, kilograms meters squared over second squared Kelvin mole, right, over. Yeah, so this is the top units, and then so this is kilogram, right, per mole. So now that starts to cancel, kilograms cancels, temperature cancels out, right? And then so you're left with meters squared over second squared. Do you? Yeah, so it's K with a negative sign, and then so that's going to cancel out with your temperature, right? Sorry, I did it kind of scribbly, because then I wrote K over here from our temperature, so that's why I was like, oh, K and K cancel. And then our moles canceled, our kilograms canceled, and then that's how we were left with the meters per second. Yeah. Remember, unit canceling will save you, especially for physics. That's what I always say. That is a good way to get through physics. All right, let's look at our last kind of sections with that. And so like we had mentioned with our ideal gas law, so we have what's called our mean free path. So we were just stating that our molecules travel in straight lines until they collide either with another molecule or the container. And then the average distance a molecule travels between collisions is the mean free path. And then as the mean free path decreases, as the pressure increases, and that makes sense, right? So we're just kind of saying, what's the distance between it has a collision? Well, higher pressure means more collisions. So that makes sense. So anytime, right, you have more collisions, anytime your pressure is increasing, that's going to decrease your mean free path, so also increasing the temperature adding more moles, that will all decrease your mean free path. And so now we can look at diffusion. And so the process of molecules spreading out from a high concentration to a low concentration is called diffusion. And the process by which a collection of molecules escapes through a small hole into a vacuum is called effusion. And so the rates of diffusion and effusion of a gas are both related to the root mean square velocity of our gas particles. So that's pretty cool. Also, just as like a fun fact, so there's these things called diffusion pumps. Well, really, let's take a look, because this is saying something, but this is actually kind of saying something deeper and cooler than we may realize. And so let's think about how to achieve ultra-high vacuum for a second. And so I'm just trying to find a vacuum pump. And so normally chemists use just like a basic little vacuum pump like this. So this can probably get you down to like, I don't know, 10 to the minus 2, 10 to the minus 3 torr. But then the question is, well, how do you get to like ultra low vacuum, right? Like let's say you're running crossbeam experiments. Well, you have to get to like 10 to the minus 8 torr. And so with that, there's these special pumps called diffusion pumps that literally take advantage of this. And so let me try to find just a picture. This is not the biggest one I've ever seen. Usually they're like pretty large things. But what's kind of cool of how they work, and it kind of tells you that, right, it has this chamber, but like the whole point of diffusion is literally what we said, is like the molecule floats around and then eventually bloop, plops into the diffusion pump and then off it goes. So it's a very slow process is kind of my point, right? It's not just like an active pump where it's like sucking, and it mentions, right, it's more this effusion, but then the diffusion pump literally has to wait for the molecule to bounce into the hole. But that's ultimately how you get to like super low pressures. And then this would take a long time too. So like physically speaking, once you busted open your vacuum chamber, because this, if you ever wanted to be a pea chemist, this is why I decided I didn't want to be a pea chemist, by the way. So you have to bust open your vacuum chamber, you fix it, do whatever you need to do with it. You put it back together, and then you have to wait like a whole day for it to pump down, and then you come back the next day and see, A, if it pumped down all the way, because then you got a leak somewhere. B, then you can fire on your machine and see whether what you fixed was fixed or whether you have to do that all over again. So you can see where P-Chem research takes a while. But yeah, it essentially takes like a good 24 hours then to get down to that 10 to the minus 8 torr. And that's essentially, right, a vacuum atmosphere where now you can run these clean crossbeam experiments and do all these fun things. All right. And so with that, a lot of what we do is then we can compare these rates of effusion. And again, like we said, smaller things are going to be moving faster. And then note your equation. So what's kind of confusing is your variables swap around here. So like maybe highlight that like I'm doing here. So our rate of A over our rate of B is equal to the inverse square of our mass of B over A there. So a little tricky, so want to make sure that we don't flop that around. And then this is kind of just our last summary of our page here. Just again, right, we had spent the whole time kind of saying, oh, ideal gas law. And then now we'll at least say, okay, yeah, we admit real gases are not the same. And of course, they deviate the most at high pressure or low temperature. And so, right, you can kind of see why that is. So just imagine, right, we said that at high pressures, we got to the physical limitation issue, and we got to the issue where they started getting so close to one another, where intermolecular forces started coming into play. So I kind of put that, well, it does tell us here, right? So again, we had assumed there were no attractions, and at these extreme conditions, attractions do matter. So they're not so far apart where we can just say, hey, there are no intermolecular forces, and then gases do take up space. And so again, right, that was the assumption with the ideal gas law, that the space was negligible. But again, at these extreme conditions, then that we can't just ignore that. And then again, we'll just kind of appreciate this chart right here. So we said at STP, our ideal gas was 22.4 liters. And then we see slight variations in our gases, again, kind of depending on compressibility. You know, ammonia is kind of close to ideal. That's kind of funny. Nitrogen is pretty ideal. So they're all pretty close, right? Just a little off. But again, in practice, we always just use the 22.4 liters. Just still fun to kind of appreciate. And so like we had mentioned, at low pressures, the molar volume of argon is nearly identical to that of an ideal gas or many other gases. And then, of course, as our pressure increases, our molar volume of argon becomes greater than that of an ideal gas, since, again, those argon atoms have to actually occupy space. And so then we get into some corrections. And so since real molecules take up space, the molar volume of a real gas is larger than predicted by the ideal gas law at higher pressures. So you can see, right, where we have this deviation. And so someone did quantify this. And so I'll just kind of show you this equation. In practice, I don't think we're actually going to use this in this class, but I want to make sure that you at least know that a correction exists, because if you ever needed this correction, if it became relevant in your research, I don't want you to be completely ignorant of it. But that being said, it just doesn't really come up in practice for us. And so again, just take it in, right? We have our ideal PV equals nRT, and then we've corrected it with this van der Waal constant. And so again, this is where it's very specific to whatever your case is. So again, you're doing research, blah, blah, blah. All of a sudden you do care. And so you would look it up for that specific gas. And then so same thing. So there's a correction for the intermolecular attractions. And so as we mentioned, so at high temperatures, the pressure of a gas is nearly identical to that of an ideal gas, right? Especially at our kind of ambient temperatures, higher temperatures, right? It's all ideal. But then once we start to get too low, then we start to talk about condensing our gases in practice. So I'll put condensing. And again, right, those intermolecular forces, IMF. And so then our pressure of gases tends to be less than that of an ideal gas, again, because those intermolecular forces are kind of holding them together. So it's not just bouncing away like an ideal gas. And so at lower temperatures, the gas atoms spend more time interacting with each other and less time colliding. So the actual pressure is less than predicted. And again, we won't test over that in here, but we can see our modification if you ever needed it. So our correction, and again, right, it's another constant that you would have to look up for whatever specific gas you're working with. And then this is considered, right, the overall corrected equation, but I'll just put, we're not going to use in here. But I still want you to be aware, right? We want to make sure we set a good foundation for y'all. So if, again, if you ever needed this knowledge, you know I'm going to go look this up. I'm going to go look up these van der Waal corrections and correct for the particle volume and the intermolecular forces. But unless you're doing very specific research, then you don't need this. Like I said, I've never like needed to do this in my life, so it would be a very specific scenario. And so then just the other thing that we want to appreciate is the deviation of our real gases from our ideal. So again, here's our ideal, right? PV over RT plot. So of course that should remain constant. And we're just appreciating that there's lots of deviation. Of course, water, we would expect there to be deviation for since it condenses pretty readily. I mean, I'm somewhat surprised by like helium and neon that they're so far off from it, but again, this kind of shows you where the corrections are necessary, but even so, I mean, pretty small deviations for the most part, but still good to appreciate. All right, I think that is the chapter. So I did bring fun stuff to kind of go over our laws again with, so I can get them going, and then I'll also pull up the homework so we can probably run through some practice problems or anything else. So I don't know if people wanted to go over MO theory or not at all before the quiz, or how we're feeling on that. Yes. All right, so we can do MO theory. So what do we want to do then? A mixed one or a charged one? So we could do, so do you want to try NO then? So let's do NO, and then let's do this for fun. I actually don't know how it'll turn out or if it'll matter or not. But let's try, we'll do a comparison. So I was saying this could be a good exam question. And so let's do it first with no SP mixing. So what does that look like? And then what if we do invoke SP mixing, right? It's one of those ones right on the line. So what would those look like? And then so while people work on that, I'm going to get our demo going. So I mentioned we were going to do a baby version of the 55-gallon can. So as much as I would love to do that, I don't know that I could get support for. Yeah, I mean, well, that's what I'm saying. Where would I even get the 55-gallon drum from? That would be fun. Yeah, yeah. Well, if anybody wants to get me a drum. Okay, so that's going to think about its life for a second. So I'll let you draw out MO diagrams for. Oops, sorry. So when looking at the homework, or at least the few chapter 9s that I looked at, most were pretty good. So, right, just always double check yourself. 1, 2, 3, 4, 5, 6, 7, 8. So that's good, right? We had 4 atomic orbitals on this side, 4 on the other. And then I haven't filled in any electrons yet, right? We're just looking at our order. Again, let's note what's different, right? So remember, when we do not have sp mixing, our pz is the lowest p1, right? So it comes after our 2 s's. So our 2s bonding, our 2s antibonding, right? That's clear. And I'm not showing the core electrons. So if you look at the homework, right, there's kind of 2 answers. And it depends whether you count the core electrons, and in that case, just so we're thinking about it, right, the 1s is way down here, right? So these are mainly focused on our atom. So this would be our 1s bonding and our 1s antibonding, but in this case, we don't care about them, and we only care about them if you're counting the total number of electrons, and then we need to start at the bottom to fill. But for the most part, right, we're just looking at the valence. So that describes the difference in electron counts. And so for this one, so nitrogen, I have 1, 2, 3, 4, 5 valence electrons, and then 6 from oxygen. So now I'm going to fill in 11. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 there. So it looks to be in our pi antibonding orbital for our highest occupied, right? So those are usually what I point out. So now take a few minutes. So see if we can do sp mixing now. Let's see if it changes it or not. Remember, all that's really happening is now this pz is going to be higher in energy than our pi bonds, right? Because essentially this becomes non-bonding when we mix. And so I'll let you kind of sketch it out, and we'll look at it again. My can's still heating up slowly. Oh, getting hot there. Grab extra ice. All right, so let's see how your sp mixing is going. Oh, I lost my. So trying, so ideally, if I were doing this, oh, sounds like we're getting boiling. Sorry, distracted by our can over there. And so technically, right, the whole point of SP mixing is this drops lower in energy from mixing, right, our PZ. So you can kind of, again, try to visually place those on top of one another, right? So the unshaded parts are kind of matching with these unshaded parts. Oh, I should have drawn that consistently. But again, it doesn't matter, just as long as the two parts in the middle are the same shade. Or I saw some people using pluses or minus conventions. That's also appropriate, right? So you could do plus plus, the signs match. So that looks good. Then we still have to have our anti-bonding orbital. And then remember the flip. So now our pi bonding is next in line, since again it's kind of more bonding, more favorable, more direct interaction compared to, so the next one. So remember, it's still formally bonding, right? So the colors match, or the signs match, whatever you guys prefer. But the point is the electron density is on the outside, so it's not really, right, a lot of bonding shared electron density. So still sigma formally bonding, right, when we do our calculations. But I always kind of like to put this non-bonding here to show the lack of electron density. And then keep going. So now our pi anti-bonding. And then, of course, our very bad combination that we paid the price for. And technically, I should have drawn this a little better. So the point was we minimize this. So even though it's anti-bonding, minimize electron density between them. And then double count that we have 8, 1, 2, 3, 4, 5, 6, 7, 8. So that looks good. Now let's fill in just our valence electrons. So 5 plus 6 once again. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So notice, right, in this case, it did not actually change the identity of our highest occupied, of our HOMO. But still good to point out. And then again, like I've kind of mentioned, this is where computational chemistry comes into play and gives us a better understanding of exactly how much SP mixing there is or is not, right? And so again, for this one, it really ends up being kind of not relevant how much mixing or not mixing you invoke, since it's the same HOMO. Does that kind of make sense to people? So yeah, does that kind of help with questions too? And so that's your quiz. So your quiz is just all like numbers and like how many electrons, is it paramagnetic, diamagnetic. So use these as your skeleton sketches, right, as your guide, or use the other cheat sheet as your guide, and then all you're doing is filling in electrons. All right, my can of water is taking a while, so feel free to ask me other questions. Meanwhile, we'll look at kind of all the contraptions I brought. So this one just shows our relationship of pressure and volume. So you can see I have this knob here, and then we have our tube and our pressure gauge. And so so it's at 6 right now. And so if I start twisting this, you can see my dial decreasing. So you can see that on camera. Again, just our pressure volume relationship. And so if I take this out to 12 roughly, and so now I'm at 12, right? So I started at roughly 2, at 6. Now I went all the way down to 12 milliliters for our volume, and now we're at 1 for our pressure. So just showing our pressure volume relationship. Okay, eventually we'll crush this can. But let's do the cool version. And by cool, I mean cold. Sorry, camera. So this isn't like the most exciting thing, but it's still fun. And so, right, you can take a balloon, of course. And then this is always fun to do with just like the little kids. And of course, your balloon starts shrinking as we condense our molecules of air down. And then sometimes there'll be like gas inside. Oh, cold. Sorry. And so obviously it reflates. So good for entertaining, like I said, small children. Do that one more time. Yay. And then I didn't bring boiling water for the balloon. Let's see. I wanted this can to really be boiling here. Just give it another minute or two. Oops. I just want to see kind of steam coming out before I try to dunk it. So you can see, right, I have the same but mini setup from the 55 gallon. So we're just doing the same thing. Oh, I can see steam coming out now. So we're just trying to get the steam going. So you probably saw earlier, right? I poured water in there. Again, trying to take advantage of water being at all three phases of matter pretty readily. So I still just wanted to see a little bit more boiling. I'll let it think about its life for another second. Have we looked at the gas laws homework? Is anything particularly tricky? I was thinking probably some of the partial pressure ones might be difficult. Okay, let's try. These partial pressure ones tend to be tricky. So I'll just do it on this page. So this is from your homework. So we have a mixture of 5.25 grams of CO and 8.43 grams of CO2 exert a total pressure of 1.75. And so what are the partial pressures of both of those? So even if we don't quite finish how to do it, kind of outline in your mind, right? How would you approach this one? What is it asking for? And so remember, if you're new to my class, all the answers should be posted under like the recitation folder if you guys haven't found that. And I have been trying to check your answers as I get them, so I'll circle and note things, but it's still a good idea to double check your work. All right, what do we think about this can? Seems pretty hot. Well, there's still a lot of water in there. I don't know if I put too much water. Okay, I guess we'll wait. We'll do this problem, and then I'll give up on the can. All right, so what do we need to do for this problem? What do we need to find? Moles, right? So kind of recall from our partial pressures, we essentially need to find our mole fractions. Sorry, trying to find, where's our partial pressure? So remember we have our mole fraction, so we need to find what percentage is each component of the total. So let's do that. We'll find moles of each. And so we have 5.25 grams of CO. And so what's our molecular weight of CO? Sorry, what did you say? 28.01. So find our moles. So about 0.187 moles of CO. And then CO2. So now 8.43 grams divided by, what's the mass of CO2? About 44. So about 0.19, I'll round it to 0.192 moles of CO2. Again, right, you can have slightly different numbers with rounding. And then, so we want to find our mole fraction of each. Although in this case, right, this is easier in that there's only two gases. So once you find one, you can take, right, 100 minus the other. That's the other one. Otherwise, we find moles of 1 over our total moles. And repeat that. So 0.187 divided by our total number of moles. And so about 49% or 0.493. So again, you can report this as a decimal or a percentage. And then you could take 1 minus that, or we can plug this in. So 0.192 divided by our total moles again. And so that does give us, right, 1 minus. So about 50.7. And so now we can multiply our mole fraction or our percentage by our total pressure. So for CO2 times 1.75. So then we have a partial pressure of 0.88 and 887 for CO2. And then let's do the same. So now 0.493 times 1.75 to get our percentage. And so about 0.863 ATM for CO there. Yeah, which was your total pressure given. Yeah, so not too bad with those. So just remember with the partial pressures, you always want to go back to moles generally of the gas. All right, let's see how successful my can crushing is going to be. I'm a little worried just because it's not boiling as much as I had hoped for. But let's see. Oh! No, it didn't stay upright, but it did crush. All right. I didn't do it that well. We'll have to do it again if you want. But that was the point. So yeah, much less dramatic than our 55 gallon, but at least it did it. So crushed by air pressure. The equation for mole fraction. So the generalized form for mole fraction is moles of A over total moles, right? And so if in a mixture that can be A plus B plus C, right? All your gases. And so like I said, luckily this one only had 2, but you could have 4 or 5, and then you got to figure out how many moles of each. All right, I think that's all the tricks I have. Show's over. So we do have our quiz. So again, I would have probably your cheat sheet, we'll call it, for your orbital diagrams of your mixing, of your not mixing. This was a pretty good review, right? Order is the thing that we care about. But like I mentioned, your quiz asks just like, is it paramagnetic? Is it diamagnetic? How many unpaired electrons? All right, I'll keep the stream going just for a second or two in case there are questions. Then I'll hand out the quiz. So obviously, you can take your break if you so desire. Yeah, exactly. Yeah, and so that's kind of the point of, like, again, research is like you can draw the diagram this way, and then you kind of find, yeah, it doesn't really matter whether it mixed or not. And then you can use computational chemistry to, like, maybe argue the energy levels and say, well, this one is a little lower, so maybe it is, like, invoking so much mixing. But, yeah, it's... Kind of, but that's where like the Lewis dot structure helps with that. And then this kind of reaffirms like, yes, now we can see like which ones are going here and there for making our double and triple bond. So yeah, we want to double check our bond order, right? So bonding orbitals minus anti-bonding, and see what that number checks out to as well. But yeah, you're on the right idea. And then all right, you got one, right? Oh, sorry, somehow I skipped you.